slide is up. I just have 5 slides. I just need to get across a couple of points to the audience, and I guess the details can come later so that I don't bore you at this hour of the day. I'm going to talk about the technology ecosystem for electric vehicles. Dr. Prabhjot talked about, I think, a fairly good portion of that ecosystem which exists today. And I'm going to talk about this in a slightly broader sense as what you have available at your disposal if you would like to perform research and development into electric vehicles. And this is something that I would really like to emphasize, because we hear a lot of talks on manufacturing, system development, infrastructure creation, all of which is good. But as Indians, we have to develop next generation technologies as well. We cannot forever import motors, we cannot forever import lithium batteries and cells, we cannot forever import powertrains, right? So we have to have a vision, right? I mean, obviously research and development is not going to hit a product which is coming out in 2019, it's already September. But a vision of what is coming 3 years down the line or 5 years down the line, right? Even a crazy vision if required. So that can be worked back to what development needs to happen today. And when that process happens, the ecosystem, which is the topic of my talk, will help you actually execute that development and realize your ambitions. So that is my talk. I have a little inset on the top right, if you take a look. I'm going to use this as an icebreaker to explain to you once again what R&D really is. Right? I'm sure everybody knows what R&D is, but what it is really. So I used to be a scientist working in the US for several years. I worked primarily for GE, General Electric, and my personal specialization was in the micro and nanotechnology domain. I kind of pioneered, ran, and executed a project where we were ultra miniaturizing power systems. Okay, so literally ultra miniaturizing. When I say miniaturizing, we actually put very high power systems on a chip. And I'm not talking about power electronics, I'm talking about traditional mechanical elements like relays and circuit breakers and things like that. I'm not going to talk about that technology today because that needs a 2-hour lecture by itself. But I'm going to pick one very interesting piece or very simple piece of that. The first question that came up when we said we are going to miniaturize power, which is a very counterintuitive thing, because normally you think high power means large things, right? And we were claiming that high power actually means the exact opposite. We want to make it very small. One major question that came up is, if you make it so small, how will you pass a lot of current through a very small wire? Right, simple question. So what does a wire do? It's a piece of copper or aluminum which transfers current from point A to point B. And that's one of the most basic functions in a power circuit. Everything else depends on this. So the basic question was this: when you have such a small wire, how will you pass a lot of current through it? And you need to pass a lot of current for high power, right? And I think this is something that's reflective of what's ingrained in our minds, in our brains. Where if you go to a shop, you ask for a 5 amp wire, it gives you a thin wire. And if you go to the same shop, you ask for a 15 amp wire, it gives you a fatter wire. Right? And the more the current, the fatter the wire becomes. And intuitively, we have kind of assumed that the logic is that you need more cross section, you need more area to pass more current. Right? And that seems to make sense. But that is completely wrong. Right? Even though it seems to intuitively make sense, that is completely wrong. The truth is the current density of any metal, I mean, especially I'm talking about the better conductors, right, aluminum, copper, and so on, is 10 million amps per square centimeter, believe it or not. So square centimeter is about this size. And the theoretical current density, the current that you can pass through metal, is 10 million amps per square centimeter. Right, which completely blows away the logic that even for a 15 amp you need a bigger cross section, right? And it actually turns out that there are 2 parts to this problem, and both parts are actually thermal. And fact, designing a conductor to carry current is not at all an electrical problem, because the electrical limit is so far out. It actually is a thermal problem, entirely, 100% thermal problem. Right? And there are two halves to this thermal problem. One is how much heat you generate. Second is how well you can dissipate the heat that you generate. Right? And the fatter wire, yes, it does help, because you generate less heat. A fatter wire has lower resistance in the first place, but you don't need it. You can send a lot of current through a very, very thin wire, as long as you can cool it and maintain the temperature. That's the only factor that you'll have to consider when designing this conductor. And that factor alone helped us solve this problem of ultra miniaturization, right? So why am I talking about this? I'm saying that because this is fundamental research, right? And it's fundamental research does not mean you're trying to find the origins of the universe all the time. It means that you're going back to the fundamentals and questioning what you had assumed all along as an obvious fact. And some very simple answers like this can come out. Like in this case, if you cool it well, then you can pass a ton of current through a micron-sized conductor. Right? So hold that thought. I'm going to come back to this in my last slide and further explain the relevance of this idea to electric vehicles. So I'll talk a little bit about Powergear. As I said, I have only 5 slides. This is slide 2. Powergear is a approximately 40-year-old company. It's headquartered in Chennai, and we have 4 verticals. I won't dwell too much on this, but the historic vertical is in electrical products. We have a niche capability in extremely high power electrical products up to 1,000 megawatts. Second vertical is what this talk represents. As I said, I was a scientist in the US, came back to India specifically to provide R&D as a service to the industry. So I wanted to set up a vertical within this company where we provide R&D by industry for industry, right, on industrial terms, friendly IP terms, multidisciplinary research, timelines and deliverables bound, and essentially research that industry likes in terms of cost sensitivity, reliability analysis, all of the stuff that comes, which is typically not classified as core research, right? All of that is included. And then we have 2 more verticals in non-destructive testing, and of course we have an electric vehicle division where we manufacture 2-wheelers and 3-wheelers. Okay, so coming back to the topic, the technology ecosystem, right? And I think this pretty much summarizes it all. So on the left you see academia, institutions like IIT and many other colleges, and then government R&D organizations, which there are lots of R&D labs like the CSIR labs, for example, which are funded by the government and also work for the industry. And then industry's own captive R&D labs, right? And industry R&D providers. So there is where we found a huge gaping hole. We could not find proper industry, real R&D providers in the market, especially in India and largely globally as well. So what Powergear did was to start an organization in that area where we, as I said earlier, we do R&D by industry for industry, where essentially is a team of full-time applied scientists working on both fundamental research and applied research. I shouldn't say the two are mutually exclusive, because even fundamental research eventually would be product oriented, right? And in the middle is people who have a home, like the research park at IIT, and there are lots of startup companies which bridge the gap. And on the bottom you see R&D related services. There's the IP ecosystem, the design engineering service ecosystem, and the manufacturing ecosystem. And on the extreme right you see the consumers of R&D, right? So what I'm trying to convey in this slide is all the components of the ecosystem that is required to perform R&D are available today, right? So all you need is to have a vision and the budget. And the vision can be flowed back today to what new technologies need to be invented. So if you need to invent a battery that can charge in 10 seconds, all we need is a problem statement, right? The rest of the ecosystem which will implement it for you is available, right? So that's what I wanted to convey in this. And a quick slide, last but one slide, on the various technologies that we have developed expertise in. We have grown based on where the market has pulled. We have not decided that these are the right technologies to grow, but over time, the market has asked for these technologies. Broadly, I won't read out the whole thing, but there's a group in electronics, including power electronics, MEMS, essentially for sensor applications, optics, materials and chemicals, electromagnetics, specialized electronics, and high power, right? And all of this, a combination of these skills maps into what is on the right, which is into any given application. So I won't read out every item in the list again, but if you take a special example, like if you take medical devices, you will be wondering what that's doing in this list here. But that also kind of maps back to the same core skills. And believe it or not, almost no medical device is actually manufactured in India. And there's a lot of companies which are biotech startups and so on, which are excellent biology companies but don't have the expertise to develop instrumentation, which is where we play, right? Which maps back to the same core skills. So this is what we offer in terms of services, starting from innovation and flowing down to detailed engineering and actual product prototyping and development. The whole chain, including supply chain, costing, reliability, and manufacturing. Right? Okay, so I'm going to close with this. Again, since this is an EV-related event, this is kind of the list of technologies we have the expertise for and are working on related to electric vehicles, right? So we are working on new battery technologies. We have a project, without giving too many details, we have a live project, multiple live projects, especially one we are doing for Boeing, which we have proven theoretically can charge instantly if you can supply that much current. But practical limitations will actually govern in how many seconds, not even minutes, and how many seconds it can actually charge from 0 to 100%. This technology is not based on chemistry at all. It is a metal-based technology, and we are in the process of developing an actual proof of concept of this. Secondly, you're talking about novel motor technologies. A lot of people I know are working on permanent magnets, synchronous machines, things like that. But when I say novel, we are, again, as I said, targeting something 5 years down the line. So we are trying to develop something that is not magnetic at all. So something that has neither permanent magnets nor copper windings, right? So a complete paradigm shift in electromechanical actuation. And then rest, charging solutions, powertrains, solar power charging, a lot of work going on in vehicle mechanics, starting right from chassis design to rollover protection, things like that, right? A lot of novelty being brought in vehicle mechanics. Okay, so I'm going to close. This is my last slide, and I have another inset here, which brings me back to what I said in my first slide, right? Again, take this in the right spirit. A lot of people are talking about coming up with the greatest battery, and a lot of people use this nomenclature saying that on a full charge, I can go so many kilometers, right? And that number could be anything, 80 kilometers, 100, 200, 300, right? So that seems to be a metric today, that how many kilometers you can actually go on a full charge. But that is something that perplexes an R&D team like us, because we don't think the two are connected, right? If you look at that simple equation, right, F equal to ma, right, and this is a technology session, so I have to bring in at least one formula here. So F equal to ma, which is the oldest equation we all know, we all learned in high school, right? What does it tell you? And the second one, of course, tells you that energy is force times distance, right? Energy is how much energy you need in that battery pack, which will take you that distance, right? And energy is force times distance. Force is mass times acceleration, right? So all this tells you that you need energy only when you are accelerating. You don't need energy to move, theoretically, right? So I don't think we have gone back to something as simple as this in terms of fundamentals. In other words, if you were to travel, we are in Chennai now, if you were to travel to Bangalore, which is about 350 kilometers, all you need to do is accelerate to whatever speed you care to accelerate to, and you need energy only for those few seconds, and theoretically you could simply cruise at that speed all the way to Bangalore and you will be there without any additional energy requirement. Practically, yes, you'll have to need some amount of energy to fight friction and air resistance, That's all you need, right? So why aren't we, for example, concentrating on mass and acceleration? Two very simple quantities, right? Dr. Prabhjot just touched upon lightweighting, which is directly touches that mass term in that equation. And that could change the whole game. It could just completely change how much energy you actually expect in your battery pack, right? Having bigger and bigger battery packs is more of a bandage solution, right? You're not worrying about the core issue of how much mass you're trying to accelerate. The second term, so mass is obvious. The second term is acceleration. And as I said, you consume energy. You need battery power only if you're accelerating. You don't need battery power to move, right? And it's a very fundamental truth. It is just food for thought. I'm not trying to solve the world's problems here, but it is food for thought that if you go back to fundamentals to something as simple as this, maybe, for example, we will design a controller that will significantly minimize the amount of acceleration that you're performing in any given trip from point A to point B. Right? And that alone could significantly reduce the amount of battery energy you need. Right? So I just want to leave you with that thought. And as Dr. Prabhjot again said, I'm going to go to the third time. We are all very excited because EV, I think, is really the next big solution. But by no means is everything that needs to be invented has been invented yet. Right? There is a lot of stuff to do. That is the advantage, that's the beauty of a nascent technology such as EV, that there is so much left to do. And there are so many opportunities. I think the next 50 years will see a lot of innovation happening in EV. Thank you.